In this video, we're going to continue our discussion of using augmented matrices to solve a system of equations. So in the last video, we talked about what an augmented matrix is, how you convert a system to an augmented matrix, and then we talked about how you would use row operations to take that matrix, convert it to a simpler form, specifically a form in which we can immediately read off whatever the solution is to our system of equations. So we looked at the three different possibilities for what a reduced form might look like. So when we take our augmented matrix, find all those ones and zeros, we end up with one of three reduced forms. Based on the reduced form we find, that tells us that we fall under one of three different possibilities in terms of what kind of solution we expect from our system. So the first form is sort of the ideal situation. The goal is to take the left-hand side of the augmented matrix and make it look like this with our ones and zeros. So 1 0, 1 0, and as we talked about last time, when we're converting our matrix to this form, that's the order that we do want to convert our values in that particular U-shaped order. Now again, this is the ideal situation because this means, yes, we can solve the system and there is a unique ordered pair that solves the system. So the first row tells us that the first variable has a value of m, whatever m happens to be. And then the second row tells us that our second variable has a value of n, again, based on whatever n actually is in our actual problem. So that's one possibility. Now the other two possibilities result from trying to get this 0 below our first one, but in so doing, clearing out that bottom row, specifically getting 2 zeros in the bottom row so that we can no longer get a 1 where we would want it. So once that happens with those zeros, again, we fall under one of two cases. So one possibility is that the entire bottom row ends up being zeros. So specifically, when we're clearing this particular entry in order to make it 0, the result is that all entries on the bottom row clear to 0. In that case, the bottom row now represents the equation 0 is equal to 0, which is a true equation. It is a true statement, but it's a true statement that leaves us kind of stuck where we can't uniquely solve for variables because essentially we've eliminated one piece of information that we originally had as part of the problem. So if that's the case, that means we have infinitely many solutions. More specifically, it means whatever is left over from the system, whatever's left in that first row that doesn't represent just zeros, that gives the relationship between the variables. So we have infinitely many solutions, infinitely many ordered pairs that solve our system, and they're represented as all the ordered pairs that would make whatever that equation is true. So we also talked about this idea of a parameter, this idea of an external variable. We choose values for this variable, but based on the values we choose, well, our actual variables in the problem have to be related via whatever that particular equation is now in that top row. So we're going to revisit this idea of infinitely many once we get a little bit further into this section. And then our last possibility is that we have no solution. So again, the idea is we wanted to get a 0 below our first one. The result of getting that 0 is that the location, the entry next to that, was also cleared and made into a 0. But in this case, if we've cleared those two entries and they both became 0, but we have something that's non-zero on the other side of our vertical line, now our bottom row represents an equation of the form 0 is equal to p, where p is not 0. So essentially our bottom row now represents a false equation. It represents a contradiction. Again, it doesn't mean you've made a mistake. It just means that somehow the original equations are structured in such a way that something like this can happen. So if that's the case, if we run into something like that, we run into something that is false, that means there's no solution to our problem. So when we're in those specific, special, simple cases, specifically 2 equations, 2 variables, we can summarize all the possibilities just based on falling under one of these 3 forms. There aren't going to be any variations. You either fall under form 1, form 2, or form 3, and then based on what happens with the matrix, you then interpret your solution from there. Now, if you have a larger system, more equations, more variables, you can't really list out all the possible ways that your system could be simplified. Even just adding on a 3rd variable and a 3rd equation automatically makes it quite a bit more complicated to list out all the different possibilities. Just because we're talking about a wider variety of ones and zeros, and in terms of the locations we can find those, particularly with the special cases, the unique solution case will always look the same. It'll always be ones along that principal diagonal and then zeros everywhere else. If you fall under that case, then automatically it means you're in case 1 in terms of finding a unique solution. These 2 possibilities are where the forms kind of get more complicated. So whenever we have a larger system, infinitely many solutions can look a variety of different ways, and no solution can also look a variety of different ways. So it's not going to be practical to actually write out all these different possible forms that we can encounter when we're talking about solving a system and running into this kind of thing when we're looking at a larger system. So instead, what we want to do is give a general definition of what reduced means and what it's going to look like, regardless of the size of our matrix, the size of our system. So this reduced form is what we also call reduced row echelon form. That's a long term, RREF. We can substitute RREF and simplify it. So reduced row echelon form has several different characteristics. As long as the matrix you're looking at fits all of these characteristics, then you can say it is fully reduced. It's in reduced row echelon form. So the first requirement to be in this form is that rows containing only zeros, if we have one of them, we might have more than one. Rows containing only zeros have to be at the very bottom of the matrix. So if they were further up the matrix, you need to transpose rows so that they're there at the bottom of the matrix. So all zeros are always at the bottom. Anything above those has to be rows that contain at least one non-zero element. Now the second requirement, the leftmost non-zero element, so far left, the leftmost non-zero element has to be a 1. So if you look at the far left on each row, the far left on each row is either a 0 or a 1. If it's something that's non-zero, then it has to be a 1. Essentially, it has to be a 1 because ultimately we can always convert it to a 1 regardless of what else is going on in the matrix. So if it's not a 1, if it's a 2, a 3, something like that, ultimately we have to convert it to a 1 in order to say that the matrix is fully reduced. So remember, that's like multiplying by the reciprocal. If it's a 2, if we multiply the whole row by a 1/2, well then that changes that 2 to a 1. Ultimately, the goal is to make sure that all of the operations that can be executed have been executed, and we have the matrix as far reduced as it can go without ultimately undoing any of the work we've already done. Okay, third requirement, the only numbers below each leftmost 1 are zeros. So if you go over to the far left in each row, find the 1. Anything under a 1 has to be a 0. Now again, that's because we can always reduce. If we can find a 1 in a particular column, that 1 can always be used to reduce and get zeros below. So suppose you had a 2 below it. Well, we know a 2 needs to be canceled by a -2. So if you take the row containing your 1, temporarily multiply that row by a -2, you can combine it and reduce anything you want below it. So once we can get a 1 in a column, that 1 can always be used to reduce anything we need below it. So that is also going to be a requirement. And then also, final requirement, the leftmost 1 in any row is to the left of the leftmost one in the row below. That's kind of a tongue twister. There's a lot going on there. Essentially what that means is if you find a row that has a 1 in it and it's the far left, then row by row by row, the ones go inward. So the top row will have the leftmost one. The next row, if it has a 1, it's got to be further in than the previous one. So a more general way of describing this is think of reduced form as a triangular form. We're focused on the fact that there is essentially a triangular shape to these 1s and 0s. So the leftmost element needs to be a 1 if it's non-zero. Anytime we have a 1, everything below it needs to be 0s. And then essentially we'll have what looks basically the same all the way along that principal diagonal. So 1, 1, 1, 1, 1, more than likely. If we have any rows with just 0s, things that resulted like that, they have to be at the very bottom of the matrix. We may or may not have them, but if we do, they need to be at the bottom of the matrix. What we ultimately don't know is what's happening above our 1s. So once we see those 1s, again, everything below them has to be 0. But we can have a variety of different things happening above our 1s in that upper right-hand corner. That ultimately doesn't have anything to do with being fully reduced. And that's where we tend to see the variety in the different forms we encounter. All of these are strict requirements for saying that something is reduced. But we can have a variety of different things up in this upper right-hand corner and still have a matrix that is reduced. Ultimately, what we'd have to be able to say at that point is, based on what I'm looking at, am I looking at a situation where there's a unique solution? Am I looking at a situation where there's infinitely many? Or am I looking at a situation where there's no solution? What we really want to do once we have a reduced form in order to make that determination is we need to know how to read back what we're looking at. In other words, once we have our simplified reduced matrix, if we can take each row in the matrix and convert it back to its corresponding equation, that is then going to give us the information we need in order to make the determination about which one of these situations we fall under. So what we really want to talk about though is how do we reduce them? Once the matrices are reduced, it's really no different than what we did before. We read off row by row what was left, and then based on what was left, that tells us which situation we fall under. But once the matrix is bigger, if there are more rows, more columns, in other words, more equations and more variables, how do we actually go about reducing that matrix? So when it was something like this, 2 equations, 2 variables, max you have 4 operations to execute. You have to get a 1, a 0, and then another 1 and a 0. That only takes 4 operations to do. But suppose you had 3 equations and 3 variables. Well, that means the left-hand side of your matrix has 9 entries, which means in theory you might have to do 9 row operations to put it in the form you want. Immediately it becomes more and more and more complicated and much more tedious to reduce by hand. So what we want to talk about is how you can do this reduction in your graphing calculator. Now, if we were to do this by hand, you will learn how to do this by hand if you ever take a linear algebra class. That's going to be one of the places where you start in a class like that. The actual algebraic procedure used to reduce a matrix is what we call Gauss-Jordan Elimination. So it's named for 2 mathematicians. We're going to avoid the actual by hand procedure, and we're just going to accomplish the same goal using an operation in a graphing calculator. I do want you to remember a couple things though in terms of the limitations of your calculator. Number 1, the calculator can find a solution, but it cannot interpret the solution for you. So your calculator can take a matrix that's complicated and it can reduce it for you. That part will be fairly straightforward as long as you know the keystrokes to follow. Your calculator can do that. But once it's reduced, you still have to understand what you're looking at. Remember, that's essentially just, can you read off what you're seeing row by row by row on your matrix? As long as you can interpret what you're seeing, then using the calculator is going to be beneficial. Now also, the calculator rarely detects errors. It can detect formatting errors. So for instance, if you use a subtraction sign where you needed to use the negative symbol, it will throw back a syntax error because you didn't type something incorrectly. But something like just typing in the wrong number, reading off the number incorrectly, typing the number incorrectly, your calculator is not going to catch something like that. It's just going to execute whatever operation you give it based on the numbers you've typed in. So errors based on carelessness, just not paying super close attention to detail, those are really, really easy to make, and your calculator will not catch them for you. So big takeaway from that is you absolutely need to check your work at every step in the procedure, particularly while you're typing in your matrix. While you are typing it in, you want to check and double check that every single entry is typed correctly before you do anything additional with your matrix. Now, doing this particular procedure in the graphing calculator is a little bit tedious, it is a little bit involved, but it will take you a lot less time than what it would take you to do things by hand. So I think ultimately you're going to like it. So if you don't have your graphing calculator out, make sure you go ahead and get it out. Make sure everything's cleared out. Now, if you've used matrices before or you've accidentally made it into the matrix menu, you may have some stuff already in there. Otherwise, more than likely, you've never actually used it before, in which case your matrix menu will be cleared. And I'm going to show you how to clear it once we actually go in and do a problem, because it's going to be a menu where once you start doing these problems a lot, things can build up, the menu can get a little bit cluttered. I do want to show you how you clear things out if you want to clean things up and sort of start from scratch. Okay, so once your calculator is on, if you notice on the left-hand side, there's a button under Math, so there's your Math button. If you look at the button right under that, it says X with a subscript, or a superscript of -1. And then right above that in blue, it says Matrix. That is where you're going to find the Matrix menu. So second, X to the -1 is going to take you into the Matrix menu. Now you have 3 sub-menus, and you can access each of them using the arrows that take you left to right. Now the matrix menu is a little strange in the sense that how we're going to use it, we're not actually going to start on the left and work our way to the right like you would normally think we would do. We're actually going to start on the far left with the Edit sub-menu. So if you have a matrix and you want to type it in, this is where you're going to type it in. So if you've never used anything before in this menu, more than likely this will be exactly what you see. Now if you've used the matrix menu before, next to these letters and brackets, it may have dimensions written out. So it might say 2 by 3, something like that. Don't worry about that. Ultimately, you can write over every single matrix you type in. And then again, I'll also show you how to clear things once you have something entered in. So anytime you want to type in a matrix, it's going to be matrix menu and then edit. So let me clear out one more time, show you how to get to it again. So X to the -1, matrix is in blue right above it. So second, and X to the -1 takes you into the matrix menu. We have names, we have math, and we have edit. So we're going to start with edit. Okay. Well, what are we going to type in? Well, here's our first example. So our directions are to solve by Gauss-Jordan elimination. Now again, Gauss-Jordan elimination, technically that's the name for the algebraic procedure you'd use to solve. But when you see that terminology, if you see it, ultimately that just means find the reduced form of the matrix and then solve the problem from there. You're going to find the reduced form of the matrix not by using this elimination procedure, but by using your graphing calculator. But first thing you need to do in either case is take your system and convert it to a matrix. Now, as I mentioned last time, you may or may not encounter this issue, but if you do want to make sure that you are in standard form. In other words, all variables are on the same side of the equation. So if you have variables on either side of the equal sign, you need to move it so that all variables are on the left-hand side. All variables need to be alphabetized. So think of it as matching variables are lined up in the columns so that when you type in your matrix, when you write down your matrix, everything will be lined up in its correct column. That's what we call standard form. Now, once you know your equations are in standard form, now it's just a matter of picking off the coefficients, the constant values, and then dropping off your variables. You can either go column by column or you can go by row. I personally like to go by column because it helps me space things a little bit better if I'm going to write a matrix by hand. So if we were to go by column, remember each column is going to represent one particular variable. So the first column for this matrix represents the coefficients for the variable x1. So we have a coefficient of 2, a coefficient of 3, and then that unwritten understood coefficient is a 1. So first column is going to be 2, 3, and then 1. Our second column is going to be -2, and then 1, and then -3. And then our third column is going to be 1, -1, and then +2. And then remember, our equal signs are represented by that vertical line. And then we're going to write the constants on the right-hand side of that line. So 3, 7, and 0. So that is going to be the matrix form of this particular system of equations. That is going to be what you type into your calculator. Okay, so we're in the edit menu. We want to type in this matrix. So highlight one of your matrices. More than likely A is already highlighted. So if A is highlighted, that's fine. Just highlight it and press enter. Now the first thing you're going to want to type in are your dimensions for your matrices. That's going to automatically format a grid for you. So notice right now it's just listed as 1 by 1, which is literally just a matrix with one element. We go rows by columns, so we want 3 rows and 4 columns. So I'm going to type 3 and then hit enter, and notice it's going to format 3 rows, and then 4 and hit enter, and now it's going to format 4 columns. Now, depending on how new or how old your calculator is, it may format it where it's a little bit more condensed like this. If your calculator's a little older, it may format it so that the boxes are larger and some of them fall off the screen. That's okay, they're all there. You can find them regardless just by using your arrows and going back and forth. So as long as your dimensions are correct, it has formatted a matrix correctly for you. Now we need to type in our elements. Each time you type one, you're going to hit enter, and it's going to go across each row, and then it'll bounce down to the next column, and the next row beginning at the first column, all the way down. So the very last thing you'll type will be the bottom right-hand corner. So type in your elements going left to right across your row. So 2, enter, -2, enter, 1, enter, 3, enter, and then notice it goes down to my next row. Okay, 3, enter, 1, enter, -1, enter, and I'm going to type something wrong here, and I'll show you why in just a second. Let's say I type 6 instead of 7. Okay, bottom row, 1, enter, -3, enter, 2, enter, and then 0, enter. And notice once you type in the last one and hit enter, it brings you back up to the top. Now, before you do anything with this matrix, you need to verify that every single element is correct. Read through the matrix you wrote and then read through the matrix you typed. Keep in mind, if you incorrectly convert to a matrix from the system, then automatically, even if you typed it correctly, you're still working off incorrect numbers. So double check everything at every step. Number 1, did you convert it correctly? And then number 2, did you type it correctly? Now we decided that's 6, that's not right. Remember, it should be a 7. If you typed something incorrectly, then just use your arrows to go over to whichever entry you typed incorrectly so that it's highlighted, and then just type over it, and then hit enter. And then notice it clears that 6, and it's going to give me the correct one, and then it's going to take me down to my next entry. Now, once you're satisfied that you've typed it correctly, you're not going to clear to get out. A lot of things in your calculator you can clear to get out. This is an actual application, so you actually have to quit to get out of it. So right above the mode button at the top, it says quit. So second and mode will take you out of that. And it saved that matrix. You don't have to do anything to save it. It's automatically saved it in whatever location you typed it in. Now we're going to go back into the matrix menu again. So second, x to the -1. And then notice right there in the A spot where it was clear before, now it says 3 by 4. It saved the matrix that we just typed in that particular location. So we use the edit menu. Here's that matrix again. We're going to work from right to left. So the next submenu we'll go to will be the math menu. This is where you're going to find all of the operations that you can apply to a matrix. So what we want here is the operation that's going to reduce our matrix, specifically the one that's going to put it in reduced row echelon form. So what you're looking for as you scroll down is going to be the RREF operation. Now you're going to have to be careful because there's two operations that look similar. There's an REF and then there's a double REF. You want the double REF. That stands for reduced row echelon form. So scroll down, highlight it, and then press enter, and that's going to put it on your home row. So it's now typed in the operation you want. Now you just have to give it the matrix that you want it to apply that operation to. So you're going to go back into your matrix menu one additional time. Now you're going to use the names menu. So edit is where you type in a matrix. Names is where you find a matrix that you've already typed in and saved. So highlight the one you want to use. In this case, we're using matrix A, and then hit enter. And again, it's going to put you on that row. So this is saying take matrix A and find its reduced row echelon form. And so if you do that, take that, press enter, notice it's going to give you a matrix. Now, immediately, this second row, far right element probably sticks out to you like a sore thumb. What the heck does this mean? Well, we talked about the letter E before, but this is not the same E. This E is an E for scientific notation. So what this actually means is negative 3.5 times 10 to the negative 13th power. 10 to the negative 13th power would take this decimal and would take its point and move it 13 places over to the left and put in a bunch of zeros. In other words, it's a teeny tiny number. When you see anything like this, I want you to interpret that as 0. It's not truly 0, but it's a number extremely, extremely close to 0. Your calculator doesn't actually execute the same kind of algebraic operations that you do, just adding, subtracting, multiplying, dividing. It has different ways that it's programmed to execute those. So sometimes something like 0 or something really small will end up kind of like this, so that, I mean, your calculator, it's not like your calculator did anything wrong, but it can't handle all the operations executed in the same way that you do them when you do them on paper. So just big takeaway here, this, which looks really, really strange, this means 0. It's technically a really, really teeny tiny number, but it just means 0. Okay, and I hit enter again to wake my calculator back up. So notice what we have on the left-hand side. We have 1s and 0s, where 1s are on the diagonal and then 0s are everywhere else. That is the hallmark of a reduced form. What we now have on the right, that represents the new far right column. So that column is going to be 2, and then remember this is 0, think of it like 0, so 2, 0, and negative 1. So this is going to be your reduced form. So 1s and 0s, and then 2, 0, and negative 1. Once you have it reduced, it's just a matter of reading off the solution, interpreting what you can see. As long as you're able to get all 1s and 0s in this form, where it's 1s on your diagonal and then 0s everywhere else, that means there's going to be one unique solution, one value for each of your variables. So our variables here are x1, x2, and x3. So first column was the x1 column. So we have a single x1, no x2, no x3. So a single x1 is equal to 2. So x1 is equal to 2. x2 is equal to 0. Don't look at the second row and think there's no solution. All we're saying is that the value of the variable x2 is equal to 0. We can have a variable taking on a value for 0. That's fine. The special cases only pop up when we have a row of zeros on the left-hand side, so be careful there. And then our bottom row x3 is equal to -1. So this is going to be the values, this is the set of values that satisfy all three equations. How could we check these? We're not going to go through it, but remember, if you were to take those numbers, plug them back into each of those equations, those numbers should make all three equations true in tandem. That is your verification that those are in fact the solutions to your system. Okay, let's look at another one. So 2x1 minus 4x2 plus x3 is equal to -4. So removing our variables, that's going to give us a 2, a -4, a 1, and a -4. And then same thing for our additional rows. So 4, -8, 7, and 2. And then -2, 4, -3, and 5. That's going to be our bottom row. So this is going to be our augmented matrix, the matrix form of our system. And we want to reduce this matrix. So we want to do this in the calculator. We're going to type it back in. So I just cleared it all out. Now go back into the matrix menu. So second, x to the -1. Notice it still has matrix A saved. Suppose you want to clear this out. Well, you have a couple of options. If you go to edit where you're going to type things in, you can actually just write over the same matrix every time. If you want to do that, that's perfectly fine. What if you don't do that and you start to accumulate a lot of things? Unfortunately, there's no way to actually clear a matrix out here in the matrix menu. Even if you hit delete or clear, clear just takes you out of the menu. When you go back in, that matrix is still there. How do you get rid of it? I want to show you how to do that before we actually do this problem. So right above the plus button, it says in blue MEM, which stands for memory. So if you hit second and plus, it's going to take you into a menu where you can clear things out that are saved into your calculator's memory. So the second option says memory management and delete. So I want you to highlight that and then hit enter. And it gives you a variety of different things that you may have typed in that you then can clear. So if you look at option 5, that says matrix. So I'm going to go down to option 5, highlight that, hit enter. And it has matrix A, and it's telling me how much space that's taking up. I don't want to keep matrix A because I don't want to clutter up my matrix menu. So I'm going to highlight it, and I'm not going to press clear. Again, clear is just going to take you out of the menu and do nothing. You're going to press delete. So press the delete button, and now that's cleared out, and you won't find it when you get into the matrix menu. So now you can press clear to get out of there. And then when you go back into the matrix menu, notice it's gone. It's cleared it out of memory and you can start fresh. If you have multiple matrices saved, you'll have to individually highlight each of them and you'll have to delete each of them one by one, but that will clear out your menu for you. So now let's type in this matrix. So go to the edit submenu first, highlight whatever matrix you want to use. I'm just going to use A again. Type in your dimensions. So rows, we have 3 rows and 4 columns, and then you're going to type your entries across the row and then row by row by row, top to bottom. So 2, enter, -4, enter, 1, enter, -4, enter, and again it goes to the next row. 4, enter, -8, enter, 7, enter, 2, enter, then -2, 4, -3, 5, and there we go. Double check all your entries, make sure it looks right, make sure you've got everything you need. And then remember, you can't clear to get out of this, you have to quit. So second and mode, quits, takes you out of there and saves your matrix. Now go back into the matrix menu. You've used edit, now you're going to use math, RREF. So scroll down until you find that. There we go, option B, RREF, hit enter. And then go back into your matrix menu one additional time, highlight A, and there you go. That's going to reduce it. Okay, so write down your reduced matrix in this case. So 1, -2, 0, 0 along the top, 0, 0, 1, 0, and then 0, 0, 0, 1. What I want you to notice here is that bottom row. Particularly on the left side of that bottom row, notice we have all zeros on that left-hand side. That is the problem. That is one of our indicators that we're under one of those special cases. So as soon as we see all those zeros on the bottom row, we know we're not going to find a unique solution. It's either going to be no solution or it's going to be infinitely many. And the case we fall under depends on what's on the right-hand side on that row. So in that case, we have zeros on the left, but on the right, notice that we have a 1. So if we read off what that row actually represents in the form of an equation, it's going to be 0 is equal to 1. So because that bottom row represents a false equation, a contradiction, that means this system has no solution. So again, your calculator, its limitations. Notice it gives you this reduced form, but that reduced form right there doesn't say I don't have a solution. Your calculator doesn't say I don't have a solution. It just gives you the reduced form. The interpretation at that point is something you have to do. So that's going to be the interpretation based on that particular set of values at the bottom. Okay, let's look at one more. And one note I do want to make, everything we're doing here is based on the TI-84. If you have an Inspire calculator specifically, your matrix menu is going to be a little bit different. I'll see if I can find you a video on YouTube and post that just to show you what it looks like doing this in your Inspire, because how you type in a matrix, how you reduce it, it's going to be a little bit different because your menus are a little bit different. So I'll see if I can find that. Your calculator will do it. You're just going to have to find those particular operations in some different locations. Okay, let's do one more. So we've seen a unique solution and no solution. Let's look at an infinitely many. So convert your system to a matrix. If you need, pause the video, take a moment, convert it to a matrix. And then when you're ready, go back in to your matrix menu. So second, x to the -1. Remember, it's still saved. You can either clear it, remember, go into memory. So second and plus takes you into memory where you can delete that matrix. Or if you want, you can just type over it. So in the edit menu, I'm going to still highlight A. I'm going to hit enter. And it takes me back into what I already typed, but I can just type over it if I want. So it's still going to be 3 by 4. So 3 enter, 4 enter. It doesn't clear anything. But I can actually just type over the entries as I go, and it will clear them and replace them with what I type. So starting along the top, working your way left to right. So 3, 6, -9, 15, and the next row, 2, 4, -6, about to type +6, and then 10, okay, -2, -3, let's see, 4, and -6. Now here, definitely if you typed over it, you want to double check. You want to take a minute, double check, make sure everything in your calculator is as you want. And there we go. Once you're satisfied, remember, quit to get out of there, and that saves the matrix that you typed. Go back into your matrix menu, math submenu, scroll down to RREF. There we go. And then go find your matrix. Remember, edit is where you type it in, names is where you find what you've already typed. So option A, hit enter, and then there we go. There's our reduced matrix. So write down your matrix right there. Got that. Now again, we fall under a special case because if you look at the left-hand side of that bottom row, it's all zeros. That's our indicator. But notice we also have a 0 on the right-hand side of that row. So if we convert that bottom row to an equation, that's now the equation 0 is equal to 0, which is a true equation. It's true, but by getting a row of all zeros, we've eliminated one of the pieces of information that we originally started with. So that puts us in the dependent case. We have infinitely many solutions. Well, we talked a little bit last video about what infinitely many looks like. Remember, we introduced this external variable, this parameter that we have control over. x1, x2, x3, those are the actual variables that are a part of the problem. T, our parameter, is a variable that we can control. So we can pick the values we want for T, but based on the values we pick, x1, x2, and x3 then have to take on specific values that are related to one another in very specific ways. So the way we're going to find the relationship among these variables is based on the remaining two rows that had non-zero values. So I want to take those two rows and I want to convert those back to equations. So my first row is going to be x1 plus x3 is equal to -3. And then my second row is x2 minus 2x3 is equal to 4. Okay, so these are the two pieces of information I have defining the relationship among the variables in this system. Everything I need to know about the system I know just from these two equations, because this reduced form of the matrix is fundamentally the same as the original. It's just a fully simplified version reduced down to its essence. So the essence of the system is what we know right here. It's the information we get from these two little individual equations. Now, how do we know there has to be a parameter? How do we know just looking at that there are infinitely many solutions? Well, in order to solve for 3 variables, we would need 3 equations. Here, we only have 2 equations. So because we have more variables than we have equations to solve, that's our indication that there is something else going on here, and ultimately we have to introduce this idea of a parameter. The parameter is going to replace one of the variables that we actually have in the system. But in this case, which one? Because we have 3 of them. Well, with the previous one we looked at where we introduced the parameter, it could have taken on the value of x1 or x2. Ultimately, you pick the one that it's going to represent, and then you solve for the remaining variable, now in terms of that parameter, what we typically use to be t. Here, we have to choose a particular variable. So the goal is going to be to solve for whatever variables are left in terms of this parameter. So I want you to think about what these two equations have in common. In other words, if we were to replace this one particular variable, then we could solve for the other 2 variables in terms of it. Well, the one variable that these 2 equations have in common is the variable x3. So we could solve for x1 in terms of x3. In other words, we could find a formula for x1 that involves x3, and we could also find a formula for x2 that involves x3. So because this is the commonality between these 2 equations, that means x3 is going to be the variable that we replace with our parameter, with our open variable. And remember, the parameter, that just means it's an external variable. We can pick whatever values we want. So suppose we picked a value of 1. Well, that means x3 would have to take on the value of 1. But then the question is, what would x1 and x2 have to be? Well, they'll be whatever they would have to be in order to satisfy these 2 relationships based on the value that I pick for t at this particular moment. So I'm going to take each of these equations and I want to solve for whatever variable is remaining. In this case, the x1 and the x2. So we've allowed x3 to take on the value of our parameter, t. So we're going to replace that with a t in that first equation. What I now want to do is solve for x1, find a formula for it that involves this variable, this parameter t. So t is added. I'm going to subtract it to move it over. And that now gives me a formula for x1 in terms of that parameter t. So again, suppose I chose t to be 1. That means x3 would be 1, and then x1 would be whatever we get if we substitute in that value in place of t. So if we allow t to be 1, -3 minus 1 would be -4. So x3 would be 1, and then x1 would have to be -4. Now what about x2? Same kind of thing. I want to substitute this new variable in place of x3, and then I want to solve for x2, the remaining variable that's part of the system, in terms of this particular variable t. So isolate it by adding 2t, moving it over, and that's going to give you a formula for x2. So again, if we allowed t to be 1, if we pick that value externally to the problem, then x2 would have to be 4 plus 2 times 1, which would be 4 plus 2, which would be 6. So if we picked a parameter value of 1, Then x1 would be -4, x2 would be 6, and then x3 would be 1. Same kind of thing if we picked maybe a 0. If we allowed the parameter to have a value for 0, the next one would be -3, x2 would be 4, and then x3 would be 0. Any ordered pair we could get, or in this case an ordered triple, any ordered triple we could get from picking a particular value of t represents one of those infinitely many solutions. So the actual solution here is this set of formulas for our 3 variables involving that external parameter, what we're calling t. So that set of 3 formulas, that's going to be the actual solution. If we wanted individual solutions, all we have to do is pick values for t, sub in the values to those formulas, and then determine what the resulting number would be in that case. So that gives us a sense of what all 3 different situations look like using the calculator to do this row reduction to get reduced row echelon form, and then we can interpret from there, particularly based on this bottom line. Once we have zeros, if we don't have zeros, that's going to indicate which of the 3 cases we fall under. Let's look at a couple applications where something like this might be handy, using a matrix to represent a system of equations, and then using the calculator to reduce the matrix and then thereby interpret our solution. So here's our first example. The Community Outreach Division at a local nonprofit organization is advertising for an upcoming fundraiser. They want to visit 400 local homes and post flyers at 600 local businesses. They break up into 2 teams to handle the workload. Team A can visit 10 homes and post 30 flyers per hour, and Team B can visit 20 homes and post 20 flyers per hour. How many hours should each team schedule in order to make the 400 visits and post the 600 flyers exactly? So they want to meet the goal but not surpass the goal. First thing we need to do is define our variables. We're going to write a system of equations to represent these pieces of information. We have information organized in a couple of different ways. So we have information about a team A and a team B, but we also have information about visiting homes and posting flyers. So things are organized in a couple of different ways. Ultimately though, what are we trying to solve for? What's the question? Well, the question is, how many hours should each team schedule in order to meet the goal? So the question boils down to how many hours for each team? Well, we have 2 teams, which means we need 2 variables. So we can pick x and y, or maybe x1 and x2. So we're going to let x1 be the number of hours that we need to assign for team A, and we're going to let x2 be the number of hours that we need to assign for team B. Well, based on these variables, we now need to write our 2 equations. We know there are 2 equations in this case because there are 2 variables, or ideally there need to be 2 equations because there are 2 variables. Now, writing the equations is usually the challenging part. Once you have the equations written, converting it to a matrix, putting it into the calculator, that's fairly routine. How do you actually write the equations correctly? Well, just a couple of hints. Ultimately, this is kind of an art. It gets easier the more you do it because you start to recognize some patterns. These kind of problems are pretty formulaic. Ultimately, you want to think of each of the equations as representing parts contributing towards a total. So the totals here are 400 houses and then 600 businesses being visited. Okay. So when we write the equations, we want to have an equation representing homes that have a total of 400 visits and flyers where there's a total of 600 distributed. So ultimately, we'll have information about each team's contribution to the total of 400 and each team's contribution to the total of 600. Another way you know you've done your equations correctly versus incorrectly. It may be tempting to say, I'm going to write an equation for team A, and then I'm going to write an equation for team B, which is very tempting to do. The problem with doing something like that is if you do something like that, you're going to have two equations where each equation only has one variable. If we just look at team A, then we're just looking at the hours we schedule for team A. The hours we schedule for team A are represented by the variable x1. Well, if we only represent an equation involving team A, then that equation's only going to have the variable x1. It's not going to have the variable x2 in it because x2 relates to the other team. If we only do an equation for team B, well, team B is represented by x2, that's their number of hours. If we just do an equation for team B, well, again, that equation will only have x2, but it won't have x1. Ultimately, we need equations with a mixture of the variables because we're looking for how the variables are related to one another, how one impacts the other, how they both contribute towards these totals. So two big things here. Your equations typically revolve around these totals that you want to find. Find the numbers in the problems that represent totals. And then also, when you write your equations, each equation needs to have a combination of variables. So if you're talking about one particular variable related to one particular category, you cannot write an equation that only contains that variable and only relates to that category. Your equations need to involve, ideally, all of the variables that you have in the problem. So in this case, our totals involve homes and flyers distributed. So if we're talking about home visits, well, we know Team A can visit 10 homes an hour, and then Team B can visit 20 homes an hour. So if you take how many homes they visit and multiply it by the number of hours they spend visiting, that will give you that particular team's contribution towards the total. So if Team A can visit 10 per hour, then 10 times the number of hours they're working will be that portion of the total of 400 that we want to reach. Team B can visit 20, so 20 times the number of hours they work. That will be the portion that they contribute towards the total of 400. So if we sum up each team's contribution, the sum should be exactly equal to 400. Now, same thing for flyers. So for Team A can post 30 flyers an hour. So 30 flyers times the number of hours they work, that's going to be their contribution towards the total. And then 20 hours for Team B times the number of hours they work, that's going to be their portion contributed towards the total. We take the sum, and that's going to add up to exactly 600. Now you might be asking the question, why would we want exactly 400, exactly 600? Well, maybe for some reason in the application we do. But your thought might be, well, as long as we meet the goal, can't we pass the goal? Wouldn't that be okay? Well, in most real situations, the answer would be yes, that would be okay. We're actually going to investigate that kind of situation a little bit later. If we're talking about not exactly meeting a goal, but at least meeting it and then possibly surpassing it, then we're not actually going to write a system of equations. We're actually going to write a system of inequalities. So we'll talk about that a little bit later, what that would look like. We'll use a lot of the same strategies, but some of the solution techniques will look a little bit different. So here we're assuming we want exactly 400 home visits, exactly 600 flyers distributed. Notice both of our equations involve both of our variables. So that means these two equations can work in tandem to give us information about these two variables. So ultimately, we could solve this resulting system in a variety of ways. We could graph if we wanted, we could do substitution, we could do elimination, or here we're going to use a matrix. So first column represents our x1s, so 10 and 30. Second column, x2, so 20 and 20. And then the third column on the other side of the equal signs, that's going to be 400 and 600. So this is a little bit smaller than the ones we've seen before. This particular matrix is the same size as what we saw in the last section, the last video. But we can use this particular RREF in the calculator technique in order to solve any type of system represented by any size matrix. So let's see, not math, matrix. I'm going to go into the edit menu. I'm going to write over A again. Now I only need 2 rows and 3 columns though, so it's going to shrink it down, but notice it still keeps some of the entries I had. Again, you can either clear out your matrix in memory or just type over your entries. That's fine. So going left to right, we have 10, 20, 400, and 30, and 20, and then 600. Double check your entries. 10, 20, 400, 30, 20, 600. Looks good. So clear out of there. Now go back into your matrix menu. Now we're going to go to math. So edit and then math. Find RREF. Okay. And then go back in one more time and select the matrix you typed in. And there you go. There's your reduced form. So 1, 0, 0, 1, and then 10 and 15. So that means x1 is equal to 10, and then x2 is going to be equal to 15. And in the context of the problem, we're talking about a number of hours assigned for each team. So that's going to be 10 hours and then 15 hours. Now, because this is an applied problem, it seems like there's a lot more likelihood that we could go awry with our actual values that we're choosing. So let's make sure that these values do in fact satisfy both of our equations. So the goal is to visit 400 homes using 10 hours and 15 hours per group, and 600 businesses, again, using the 10 and 15 hours per group. So team 1 can do 10 homes an hour, and then team 2 can do 20 per hour. So 10 times the number of hours assigned to team 1 plus 20 times the number of hours assigned to team 2 does in fact add up to give us our total of 400. Now what about the flyers? So 30 per hour times the 10 hours that are scheduled plus 20 per hour times the 15 hours that are scheduled. And again, that's going to add up and give us 600. So that confirms that these two values do in fact solve our system, and we have met the goal described in the problem. Now let's look at one more example, a slightly more complicated example. Don't be overwhelmed by all the writing. We'll talk about what all of this means. Again, it's the same kind of situation, but what we haven't seen so far is a situation where we have a different number of equations than variables. We can have situations where we run into a possibility like that. Typically, we're going to have more variables than equations. If that's the case, remember the rule is to solve for a specific number of variables, we need the same number of equations. So if we're missing equations, that means somehow we fall under a special case and we can't uniquely solve for the individual values for our variables. So I want to look at a situation where that is going to come into play. So let's cover up a little bit and just start small. So here's our example. A company that rents small moving trucks wants to purchase 25 trucks with a combined capacity of 28,000 cubic feet. Now, 3 different types of trucks are available. A 10-foot truck that can carry 350 cubic feet, a 14-foot truck that can carry 700, and a 24-foot truck that can carry 1,400 cubic feet. And then the question is, how many of each type of truck should the company purchase? Now, this particular one is a little bit misleading because as it turns out, there's some numeric information in here that we don't actually need. What we do need, though, is to identify the totals here. So just like with the visiting homes, visiting businesses, we want to identify the totals here because the totals are going to give us information about the equations we're going to write. So we actually have 2 totals here. So the first total, we want to purchase 25 trucks exactly. And then the next total, we want to purchase them so that we can carry exactly 28,000 cubic feet. Now, what's the information here that's not important? The truck length is not actually going to be important. Notice we don't have any information, any total corresponding to the length of a truck. The 2 totals we have are the number of trucks we want to buy and then how much we want to be able to carry with this fleet that we purchase. We don't actually have any totals related to the length of a truck. So you can in a sense think of that as extraneous information. That allows us to differentiate between the types of trucks. We've identified them uniquely based on their length. That gives us 3 different types of trucks, but we're not actually going to use the values 10, 14, and 24 in equations in the actual problem. What we're going to use are the numbers of trucks and then the carrying capacity of each type of truck. So the question here is going to tell us what our variables need to be. The question is, how many of each type of truck should the company purchase? So we have 3 different types to purchase from, and we want to know how many we should get. So that means we have 3 different variables because we have 3 different types of trucks we can purchase. So X1 is going to be the number of small trucks, X2 is the number of medium trucks, and then X3 is going to be the number of large trucks. So again, we want to use these variables and we want to combine them in such a way that we're creating equations that relate to our totals. So our 2 totals here, again, we want a total of 25 trucks and we want a total carrying capacity of 28,000 cubic feet. Well, we know X1, we know 10-foot trucks can carry 350, 14-foot trucks can carry 700, and then 24-foot trucks can carry 1,400. So when we take all the trucks we buy and how much each of them can carry, we need that to add up to be exactly 28,000. So in terms of the total number of trucks, if we add up the number of each that we buy, it needs to add up to exactly 25. We want to purchase 25 trucks. Maybe we have 25 parking spots. I don't know. And then for the carrying capacity, if we multiply the capacity of each type by the number that we purchase, that will be, again, that portion of the total. So kind of like with the previous problem we looked at, 10 per hour times the number of hours was that portion towards the total of 400. Now we're looking at subtotals contributing to this total of 28,000. So 350 for the small truck times the number of small trucks, 700 per medium truck times the number of medium trucks, and then 1,400 for the large truck, again, times the number of large trucks. So add up all of these subtotals and it adds up to our total that we need of 28,000. Well, that's all the information we have. Again, we don't have a total about how long we want our fleet to be if we line up our trucks nose to tail. So the length, even though it looks like it might be an important value here, the length is actually extraneous information. But once we have those 2 equations, that's everything. We don't actually have any additional information in this problem with which to write another equation. So that's it. We have 3 variables, but we only have 2 equations. So that means when we write this particular system, it's going to have 3 columns, 1 for each of our variables, but it's only going to have 2 rows because we only have 2 equations. That's okay. Just write it down as is. We've interpreted everything. We've written everything in terms of an equation. This is all the information we have, and we're going to work off of that. So our first row, 1, 1, 1, and 25, our coefficients for our variables, and then 25. And then the second row, 350, 700, 1,400, and 28,000. This is one of those spots where writing column by column may be beneficial, because if you just start with the first row, the ones you'll probably space pretty closely together because they don't need much space. But as soon as you have to write the numbers that go below them, you'll recognize that you need some extra space. So by writing 1 column at a time, your spacing will be a little bit better when you actually write the values in your matrix. So let's type that in and let's reduce that. So I'm going to go back into my matrix menu, edit, and I'm going to just write over this one. So now we have 2 rows and 4 columns. So across the first row, we have 1, 1, 1, and then 25. And then the next row is 350, and then 700, 1,400, and 28,000. Okay, double check your entries, make sure that looks right. And then you want to reduce that. So math, RREF, back into your matrix menu, select the matrix you already typed, And there you go. So notice again, we have 2 rows, we have 4 columns. So once it reduces, it's still the same number of dimensions. We still don't get 3. But what that ultimately means is we're not going to be able to get a matrix in a form where we can uniquely solve for individual values for the variables. This is what we have. So since this is what we have, this is all of this fully reduced. Structurally, they are the same. They look different, but this matrix and this matrix are row equivalent. They give us the same information. So what we need to do now is convert this reduced system back to equations. So our first row, we have x1 minus 2x3 is equal to negative 30. And then our second row, x2 plus 3x3 is equal to 55. So that's all we know. We don't have enough information to solve uniquely for all 3 variables, but we do have a concrete relationship among all 3 of them. So because we're stuck here, we don't have a no solution situation. We don't have some equation that suddenly pops up that's not true, but we don't have enough information to uniquely solve for all 3 variables. That means we're in one of those infinitely many solutions cases. So we're going to introduce a parameter in order to represent all the different possible solutions. Now, just like the last example we looked at that involved infinitely many solutions, we have to strategically pick which variable is going to be replaced by the parameter. The goal is to have a formula for every single variable in terms of this parameter. So if we have 2 equations and we're going to have to replace something in each of those equations, then we want to replace whatever's going to be common among those 2 equations. So in this case, the common variable is going to be x3. So we can solve for x1 in terms of x3. We can solve for x2 in terms of x3. So x3 is going to have to be the variable that we replace with our parameter t. So we're going to replace the x3 with a t. So I haven't worked it out here. You may want to work it out on your own. You may be able to visualize what's happening though. So for our first equation, our x3 becomes a t. Now we want to isolate our x1, so we want to move this term over from the left to the right-hand side. So add the new term to t and move it over to the other side. So that's going to be negative 30 plus 2t, or alternatively, you could write 2t minus 30, same thing. Now, same thing for the one below. We replace x3 with our parameter t, solve for x2, okay, so we want to get it by itself. So take this term, which is positive, subtract it to move it over. And so we have x2 is equal to 55 minus 3t, or negative 3t plus 55. So out of the context of the actual problem, any value for t, and then the associated values that we get for x1, x2, and x3 represent a solution. But because we are in an applied situation, we have to be a little bit more careful. There are certain values of t that wouldn't actually make any sense here because we have to think about what t and therefore x3 represent. So x3 is going to be the number of 24-foot trucks. There are 2 different kinds of numbers here that don't actually make any sense. Now, normally t can be whatever we want. It can be positive, it can be negative, it can be integer numbers, it can be numbers with decimals, it can be anything we want. But some of those numbers are not actually going to make any sense here because we are in an applied real-world context. So one type of answer here that doesn't actually make any sense is a negative number. If we were to allow t to be a negative number, then we would have x3 is equal to a negative number. Well, x3 represents the number of trucks we're buying. Can we buy a negative number of trucks? Well, of course we can't. So because x3 represents a number of trucks we're buying, we can't buy a negative number of trucks. So t cannot be a negative number, which means we also can't plug in negative numbers here. So t needs to be 0 or larger. We could certainly buy 0 trucks, but we couldn't buy a negative number of trucks. Now, another type of number that doesn't actually make sense here is any number that's not an integer. We can't buy half of a truck or a third of a truck. We have to buy a whole number of trucks. So we could buy 0 trucks, we could buy 1 truck, we could buy 2 trucks. We can't buy 1.5 trucks though. So because we are in an applied situation, there are some additional constraints on T that aren't readily apparent just looking at the matrix and just looking at the formulas for determining our values that we got from that reduced system. So we need to apply those particular constraints in order to refine our answers and think about what the actual answers could be. So again, based on the context of the problem, all values need to be non-negative whole numbers. So T, whatever we pick for T, has to be a non-negative whole number. And then the resulting values for x1 and x2 also have to be non-negative whole numbers. So let's see what the effect is on all of the values in this problem. So T definitely has to be greater than or equal to 0. Okay, so that means x3 will be greater than or equal to 0. That's the number of 24-foot trucks we're buying. We can't buy a negative number of trucks. We can buy no trucks, but we can't buy a negative number. So T has to be greater than or equal to 0. Well, x1 also has to be greater than or equal to 0. It also represents a number of trucks that we're buying. So that means the expression related to x1 also has to be greater than or equal to 0. So 2t has to be greater, or 2t minus 30, has to be greater than or equal to 0. We want to solve for t and see what the implications are for this parameter based on the fact that this expression has to be greater than or equal to 0. So we want to isolate t. Now, isolating t, something like that, in an inequality is almost the same as doing an equation, with one exception, which we'll look at in a minute. But otherwise, you just move things left and right, just like you would in any situation to isolate your variable. So add 30, move it over. So we have 2t is greater than or equal to 30. And then divide by 2. Okay, so divide both sides by 2. So that means t is going to have to be greater than or equal to 15. So in order to fit the basic context of the problem, t has to be at least 0. But in order to also work with this expression we have for x1, we now know that t has to be greater than or equal to 15. If it were anything smaller than 15, then x1 would end up being a negative number, which means we now run into solutions that don't actually make sense in the context of our problem. Now x2 also needs to be greater than or equal to 0 because again, it represents a number of trucks that we're buying. So we want to apply that as well to the expression representing x2. Now here's where we run into kind of a special case involving inequalities. So let's look at this. So start out like normal, we want to isolate t. In this case, we're going to have to subtract 55 to move it over. So we have negative 3t is greater than or equal to negative 55. So we need to divide out that negative 3 that's being multiplied. Red flag. Here's where we have to do something special. Whenever you have an inequality and you multiply or divide by a negative number, you must flip the inequality sign. You have to flip it. It changes directions. So a greater than or equal to symbol when you divide by negative 3 is going to flip and become a less than or equal to symbol. Now you execute the division like normal, but you just have to remember to flip the inequality sign since you're dividing by a negative number. So negative 55 divided by negative 3, well, the negatives are canceled, and that'll give us 55 over 3. Now 55 over 3 doesn't mean too much in the context of an actual problem, so it'll be helpful to think of what that really is in terms of a decimal. So 55 divided by 3 is going to be 18 and a third. Okay, now can we buy 18 and a third trucks? No, we can't buy 18 and a third trucks. We also can't buy more than that because we know that t has to be less than this amount. So the closest number that we could have that would actually make sense for t in this case would be 18. So this would be rounded off to 18 in order to deal with this issue that we need all non-negative whole numbers. So if we put all of this together, all of these things that we've determined based on the fact that our variable values need to be greater than or equal to 0, and they also need to be whole numbers, this gives us some specific requirements and some specific constraints that will narrow down the situation. So we know that t has to be greater than or equal to 15, okay? But also t has to be less than or equal to 18. So it's no smaller than 15, but no larger than 18. It has to be between them. So our formulas are still correct. These are still going to be the formulas we use to determine possible values that we could purchase in terms of our different numbers of trucks. But there aren't actually infinitely many combinations that work. The only combinations that work are going to be the ones that result from values of t that fit within these boundaries and also are not fractional numbers. Remember, there are two requirements. In this case, we can't buy a negative numbers of trucks, but we also can't buy a fractional number of trucks. So t, the value we pick, has to be between 15 and 18, including possibly 15 and 18, but it's also got to be a whole number. So the different quantities we can actually buy different combinations of trucks in order to meet the goal of buying 25 and having a total carrying capacity of 28,000. These formulas are going to express the possibilities, but we'll only get an actual solution to the problem when t is between 15 and 18, including 15 and 18. Again, we can't have fractional numbers though. So that means exclusively 15, 16, 17, and 18. Those are the values that we could have for t that would result in an actual solution to this particular problem. So just to show you what this really means, if we think about answering the question, how many should we buy? You have to actually answer the question, how many could we buy? Well, we could buy any number as long as the numbers are related in this way and t has a value of 15, 16, 17, or 18. So what's one possibility? Well, suppose we let t be 15. That means x3 is going to be 15. Remember, x3 is the number of large trucks we're going to buy. So that means we're going to buy 15 large trucks. Well, how many small trucks? x1 is the number of small trucks. Well, if we plug in 15, that's going to be 2 times 15, which is 30, and then 30 minus 30 is going to be 0. So in that case, we actually wouldn't buy any of the small trucks. It didn't say we have to. We can buy 0, we just can't buy a negative number of them. Now again, what if we have 15? How many medium trucks do we need? Well, that's going to be negative 3 times 15. Do this in the calculator if you want. Negative 3 times 15. And then we're also adding 55 to that. So that would be a total of 10 trucks. So if we choose our parameter value to be 15, then we're going to buy 15 large trucks and we're going to buy 10 medium trucks. Notice 10 and 15 and 0, those add up to 25. And if you were to take the carrying capacity for your medium truck, which can carry 700, and then your large truck, which can carry 1,400 based on how many you purchase, it's also going to add up to exactly 28,000. It's the same kind of thing for 16, 17, and 18. With 16, that'd be 16 large trucks. 2 times 16 is 32. 32 minus 30 is 2, so 2 small trucks, and then another associated value of medium trucks. So any possible combination we could get with the numbers 15, 16, 17, and 18 represent a solution. So as you can see, there is a lot going on with an example like this. This is a very multi-layered, very technical kind of example. So I strongly encourage you, even if you don't revisit a lot of examples, revisit this one, print out the blank notes, and try to work through this particular problem start to finish. Of course, you have the reference here, but try to work through it and make sure you can think through the structure of the problem. How do you identify the variables? How do you write the relationships among the variables? Once you have those equations representing those relationships, we now know how to convert to a matrix, use that matrix in order to solve. But the next portion of the problem involves interpretation based on the real world context. So once we put problems into this real applied context, we do have to think about the kind of constraints we have in real life. In a lot of situations, negative numbers don't make any sense. We can't have a negative dollar amount if we're talking about buying something. We can't have a negative number of trucks in this case. In this case, fractional amounts didn't really make sense either. You can't buy a fraction of a truck. So you have to think about the kinds of effects that those particular constraints have on a problem. Interpreting what those particular constraints mean can often take something where we have infinitely many solutions and then narrow it down to something where we actually can define some concrete solutions. So spend some time working through this one again. Make sure you can think through all of the different steps in the process, and then of course how you interpret the problem in a real world context.